Hey, all, how are you doing?
Good.
Good. Is anyone here still? All right, guys. Today we're doing the last section in chapter 11. We'll quickly try and finish the stuff we didn't quite finish yesterday. And then we're going to do the last section in chapter 11. And then I pair 11 and 12 up for the first test. 12 is short. So I would say the next test is somewhere near 2 weeks from now, but I haven't looked. So it's on the calendar on the website, and you guys can go look, or I'll try and look it up and try and remember to remind you guys. But it's coming up in maybe 2-ish weeks. Your second problem set's due Friday over 11.4 to 11.6. And Thursday is a tutoring day. So if you're having questions on stuff, Thursday would be a good day that you guys could ask that stuff. But today we're going to finish up the last couple examples from yesterday's notes, and then we're going to do the last, oops, that's not what I wanted. And then we're going to do the last section in chapter 11. So where we ended yesterday, I believe, was we had gone through 3 of the 6 quadric surfaces. So we ended with the hyperboloid of 2 sheets. The next one is the elliptic cone. So kind of like all the other ones, we can start with a familiar 2D conic section. In this case, we're going to start with, you see elliptic, an equation for an ellipse, x squared plus a squared y squared, over b squared. The only difference is we're going to start with an ellipse with a 0 on the left, which really isn't an ellipse, right? That's a point. There's only one place where that thing will be true, and that's x equals 0, y equals 0. But it's similar to the equation for an ellipse, and it will become more than a point when we just add in, similar to what we did in getting the hyperboloid of 1 sheet, we'll add in a minus z squared over c squared. Okay, if we added a plus, that's still just a point. There's only one place that'll be, so that's not really a useful one. But minus will give us different x's and y's that could make this thing true, since I'll have that positive x squared plus y squared, and a minus the z squared part. I can get 0 with different stuff there. So this is an elliptic cone. It's essentially a cone. And again, just like we looked at yesterday, I could switch where the negative is, and you're still going to get a cone. It'll just change the orientation. It'll change which way it faces. It's like these would all be cones. It's just one would kind of open along the z-axis, one would open along the y-axis, and one would open along the x-axis. And so you'd have all cones, though. Okay, so the only difference is with this equation, because everything's squared, you'll actually get a top one and a bottom one, a positive cone and a negative cone. So you actually get the 2 different cones. Our traces are ellipses, in this one, parallel to the xy plane, but it all depends, right? In this one, if we plug in constants for z, right? If this was a constant and we added it to the other side, that would be an ellipse, right? X squared plus Y squared equals some constant. That'll be ellipses. If we plug in constants here and moved it over, that would be a hyperbola. If we plugged in constants here and moved it over, that would be a hyperbola as well. That's where those traces are coming from. Really, in the X, Y, and XZ plane, you've got lines, right? If you look at it. So like if we had X squared plus Y squared minus Z squared equals 0. If we let X be 0, oops, we have Z equals plus or minus Y, right? 2 lines. If you do the same thing and you let Y equal 0, you'll end up with 2 lines going this way. So those are the red lines seen there. Parallel, if you move out, you'll end up with hyperbolas. But yeah, that's your cone. Okay, elliptic paraboloid. This is another one that people get pretty used to. It's kind of like a parabola in 2D, where you guys, I feel like that's one of the functions you guys probably are most familiar with is parabolas. So again, elliptic, we're going to start with something similar to an ellipse. But again, think of a 0 on this side, so it's technically a point. But we can get ellipses if we add something to it, and what we'll do is we'll add a Z over here. And like everything we've seen so far, you could switch up which one is, oops, squared and which ones are, or which ones are squared and which one is not. Those would all be elliptic paraboloids. They're just going to open facing different ways. Okay, so basically what you'll have is two positive squared things equals one that's not squared. And that'll give you your elliptic paraboloids. And so I don't memorize these things. Okay, I really look at these as, what if I plugged in Y equals 0? If I plug in Y equals 0, I have a parabola, right? In the XZ direction, I've got a parabola. If I plug in X equals 0, oops, then I have a parabola this way. So think I've got parabola, parabola, and that's giving me my shape. And then if I were to plug in constants for Z, I would get circles, right? X squared plus Y squared equals 2, X squared plus Y squared equals 3. I'd get those, or ellipses, I guess, going around. And so that's how I usually think of these. I don't really memorize them. I just think about plugging in stuff and thinking about what those 2D equations would look like and visualizing then the 3D one as well. Okay, and then the last one is the hyperbolic paraboloid. This one is probably the hardest to draw. And for some reason, people mess it up. I think it's because people don't like hyperbolas. Most people are pretty good with ellipses or circles, but not so much hyperbolas. So we're going to start with a similar equation to a hyperbola. Again, only difference is it's 0, which again means it's only the point 0, 0, 0. But we're going to do like the last one and add Z to this side. And just like the last one, we could switch it up and we could let Y equal X squared minus Z squared, or Z equal Y squared minus X squared, or X equals Y squared minus Z squared. You could kind of switch up which single one is not squared, which two are squared. You could even switch one's the negative and the positive. Okay, and it's just going to kind of change the orientation of your hyperbolic paraboloid. And then just this one I forgot to change this as hyperbolic. Oops. Okay, so I graphed Z equals Y squared over B squared minus X squared over A squared. And so you get this weird thing. Well, notice if I let X squared in this one be 0, I have an upward facing parabola in the YZ plane. If I let Y equal 0, I have a downward facing parabola in the XZ plane, right? It's going to be negative. And then if I let Z be constant, parallel to the XY plane, I'm going to get hyperbolas. Those are kind of the sides of this thing. It's often called a saddle. because it looks like a saddle. Right? If you've ever seen a saddle, ridden a horse or whatever, this looks like a saddle. I can't draw these at all. Like, not at all. Mine, I cannot figure out how to make them look 3D. Some people are really good at that. I am not. So that's the last one. Okay, hyperbolic paraboloid. So you have those 6. You don't really have to memorize them. The more you can kind of understand, the better, but it's not a memorized thing. Okay, it's not important to have it memorized. Okay, so we're going to go to today's, which is going to be cylindrical and spherical coordinates. It's the last section in chapter 11. For now, we're just going to kind of practice using them. Their real use will come up in integrals. Okay, if you think about last year, when we, towards the end of the year, we had to integrate things like 1 minus x squared. And we would use trig substitution, right? We'd draw a little triangle. We'd say, this is 1, this is x, this is square root of 1 minus x squared. And we'd come up with, come up with sines, cosines, tangents, secants, whatever we need, substitute those in, simplify, be able to integrate. And it was one of our more advanced techniques. It was kind of one of the harder things. Some people never really got it down very well. With cylindrical and spherical coordinates, we often can avoid having to do that. And other really complex integration techniques, we can avoid them if we convert to a different coordinate system. So that's why we will end up using that in this class. Okay, in other classes, there's other applications. In this one, it's to kind of simplify an integral. That'll be the main purpose of these things. So cylindrical, most people think cylindrical is not super difficult because it's essentially the same thing as polar. So as long as you have a decent understanding of polar, cylindrical is not hard to figure out. We'll have an r, a theta, and a z. So polar is just r and theta, right? That's basically only in the xy plane. So we basically can get anywhere we want in the xy plane using polar, and then we just go up z or down z. Oops. Okay, so we have x, y, z. R is just your distance from the origin in the xy plane. Theta is how much we've moved around from the positive x-axis. And then z will go up or down and get to a point. Okay, so same exact r and theta, and really the same z as we have in rectangular. So not a big leap from understanding polar to getting cylindrical coordinates, which is good because that's the one we use the most. We use a lot of cylindrical. Okay, so say I want to be able to graph it. I'm not going to grade your graphs, but again, we're working towards kind of understanding what's happening here. R equals 4. I would kind of go out 4 units. I usually go out along the x-axis. You could go out along the y-axis, but just know that your angle is measured from the positive x-axis. So you're going to have to do it from there. Theta is 5 pi over 6, which is going to put us in the second quadrant. Okay, so I went 4 this way. I went 5 pi over 6 radians around. And then I'm going to go up, straight up 3. 1, 2, 3. 3 units vertical. That should be a vertical line. And that's kind of how we get their graphing. Okay, graphing points. It's the same location as a rectangular coordinate, a specific one, but it's not, it's more about the path we use to get there. And just like with polar, polar allowed us to graph like, weird shaped things. Cylindrical is the same. There's, it allows us to graph around things with curves and loops and things as cross sections. Okay, if you think of certain surfaces that have cross sections that are loops or circles or whatever, it can make those things a lot more simple, Okay, so our main thing is not going to be graphing these, but that you can convert. And so again, if you remember your polar conversions, this is the same thing. It's very simple to do these if you remember polar. So x is r cosine theta. For us, x is still r cosine theta. Y is r sine theta. Well, again, in cylindrical, same thing. Z is just z. Okay, z, you don't have to change. The z in rectangular is the same z as it is in cylindrical. Going the other direction, r is just a distance, so you could either think of it as a distance formula from the origin to your point, x, y, or you could do it as a Pythagorean theorem. But it's just the square root of x squared plus y squared. Okay, theta, again, you could think of it as a use right triangle trig, and what it's going to be is the inverse tangent of y over x. Or you could think of it like the unit circle. Just remember that those are, because of the limitations of arctangent, you're going to get angles in the first and fourth quadrant. So you may need to think of how it's like a reflection to get it to the other side if you have a coordinate that's in the second or third quadrant. And then again, z is z. So these are the main things you want to have. You don't have to memorize really in this class. Memorization was mainly for the AP test, which you guys in the end didn't really have to memorize because you took yours online. But normally for the AP test, we don't have a memory sheet. So that's why last year we hammered memory stuff so much. I feel like in the world we live in, you can look up formulas pretty easy. I'm more concerned with you being able to apply those formulas and understand them. So if you don't have them memorized, just make sure they're in your notes. You guys can use notes on your test. Just make sure they're in your notes and you can use those notes. Yeah. Okay. Cylindrical conversion. So say this is the coordinate we just plotted a second ago. If we convert those to rectangular, we should be able to get to the exact same location along our x, y, and z axes instead of using r's and thetas and stuff like that. So x is r cosine theta, so 4 cosine of 5 pi over 6, which is going to be 4 times a negative root 3 over 2. So negative 2 root 3. Y is 4 sine 5 pi over 6, which is 4 times a half. So 2. Z, we don't have to do anything. Z is still just 3. And so if we wanted to get there with rectangular coordinates, we would go x backwards. Okay, this is x, y, z. We'd go backward on the x-axis, negative 2 root 3, and then we'd go over on the y-axis 2, and then we'd go up on the z-axis 3. So we'd go 2 root 3 this way, 2 this way, 3 this way. Okay, and we should be in the same location. So every point you plot, you could do it in either coordinate system, and it should be able to get in the same location. Okay, going the other way, which this will be more what we usually do is convert rectangular to cylindrical, because usually we'll have like an integral in rectangular with x's, y's, and z's, and we need to figure out, it's really hard to solve in x, y's, and z's, but it would be really easy in r thetas and z's or something. So here I have it plotted with rectangular, moving 1 in the x direction, root 3 in the y direction, and then 2 in the z direction. We can get r by taking the square root of x squared plus y squared, so 1 plus 3, so that'll be 2. We can get theta by doing the inverse tangent of y over x, so root 3 over 1, which that's going to be pi over 3. And then z again doesn't change. And so we come out 2 units, go around pi over 3 units, and then go up 2 units, and we could get there in the same location. Okay, so a big part of for us using cylindrical coordinates will be recognizing when and why we would use them. So in general, Obviously, they're good for cylinders. Okay, surfaces of revolution, anything that has cross sections that are circles, okay, or at least parts of circles. When I see loops, cylindrical is obviously a lot of times going to make it easier. So like this first one, that's a cylinder. So if we think back to yesterday, this is a cylinder with a radius 3. Remember, if I have two variables, it's a cylindrical surface. The generating curve here is a circle, meaning it's a cylinder. And if we were in rectangular coordinates and I wanted to do an integral, I would do like y equals the square root of 9 minus x squared, sorry. And then I would have to do trig sub, right, to do an integral there. I would have a trig sub problem, which again is generally something we're going to try and avoid. If I convert this to cylindrical, this one's easy. Anywhere I see like x squared plus y squared, or something like a square root of something squared plus something squared or minus something squared, that's where I'm seeing like circles. When I see that in an equation, I'm seeing circles. So x squared plus y squared is r squared. 9 stays 9. So this is just r equals 3. So we could either integrate a constant, which is really easy. That's one of the easiest things we can do. Or we could integrate using trig sub on a circle, like we have up there. So obviously a lot easier to do this. Similar idea there with the next one. This is an elliptic paraboloid. Right, I have z equals x squared, which is a parabola. Z equals y squared is a parabola. So think the two cross sections are parabola this way, that's what's giving me that paraboloid. If I plug in constants for z's, I've got those circles going this way. And again, I could solve like z equals the square root of 1/4 x squared plus y squared. And we haven't even started integrating in higher dimensions, but that's going to be a difficult integral. Again, that's going to be a trig sub problem. Instead, we could see that we've got an x squared plus y squared, that's r squared, equals 4z. So r equals 2 square root of z. That's a power rule problem, right? Z to the 1/2, I can integrate that really easily. That's a power rule. Versus up there, the equation in rectangular's got a bunch of stuff going on. It's going to be a harder integral. So that's kind of what we're going to start wanting to recognize when we get to integrals. Okay, x squared plus y squared equals z squared. That's a cone. Which again, I could solve this. Z equals the square root of x squared plus y squared or something. That's going to basically be a similar issue. Oh, I just realized on that last one, this should be not square rooted. That's going to be a similar issue on the last one, though. It's going to be difficult to deal with because of the x squared plus y squared part. But notice x squared plus y squared is r squared. Z squared is just z squared. So this is r equals z. And then this last one, this is a hyperboloid of one sheet, which is that thing that's kind of like a cylinder, but it curves in. Similar to all the other ones, solving this is going to give me a hard integral to deal with. But if I plug in cylindrical, I have r squared minus z squared equals 1. R equals the square root of 1 plus z squared. Unfortunately, even with cylindrical, that's probably going to be a trig sub problem, but it's still going to actually be a lot simpler than the other one. So if I see kind of those circle cross sections like we have in all these shapes, that's usually where I'm thinking that cylindrical would be useful. Okay, things with loops or circles or whatever. Most of the time, if it doesn't have them, it'll make it worse. So most of the time, if you've got like we had y equals sine x yesterday, and we had that surface that was kind of a wave, That is not going to get better by turning it into cylindrical. So it's not, you wouldn't want to use it unless you kind of saw those circular pieces. Okay, but some things that aren't circular aren't especially difficult in cylindrical. So vertical planes intersecting the z-axis are pretty easy. This is x, y, z.
I'm gonna go get some food.
Okay.
I'm gonna go see if these guys will come to our trailer.
Huh?
Look, there's guys power washing the trailer.
I didn't think you were allowed to do that. Okay, so say we had this vertical plane. That's also fairly easy to express in cylindrical coordinates, because think about every point on the plane has something in common. They share the same theta, right? I could get like here by going some r out, that theta around, and then up a certain z. I could get out here by going some r out, some theta around, and up z. But notice the thetas are all going to be the same at every single point. So this is going to be theta equals a constant. If I were to graph theta as a constant in cylindrical coordinates, I'm going to get a vertical plane going through the z-axis. Horizontal planes are also easy. Okay, so if I've got this horizontal plane that just cuts through at some point, all the points on that plane have the same z. So if I'm in cylindrical or rectangular and I graph z equals 4, I'll have a horizontal plane at z equals 4. If I graph theta equals pi over 2, I'll have a vertical plane along the pi over 2 radian line or whatever. Okay, so this will be kind of the biggest thing we use is this type of stuff, converting rectangular equations to cylindrical. So again, this is a cone. And if we convert it, we have r squared equals 4z squared, r equals 2z. And you should already be able to see that looks simpler than x squared plus y squared equals 4z squared. For one thing, one of the variables is gone. You only have 2 variables instead of 3. And you don't have squared things and all that stuff. So it's gonna be a lot simpler to deal with. This one right here is not gonna get simpler. It actually doesn't get easier or harder. It stays relatively the same. So yesterday, remember this is called a cylindrical surface. So say this was x, y, and z. This is a cylindrical surface. Cylindrical surfaces can be identified when you've got 2 variables, like we have here. What I think of this as is in 2 dimensions, x equals y squared is a parabola along the x-axis instead of the y, right? So it'd be a parabola like this. And what makes it cylindrical is if you were to take it in 3 dimensions, you're basically getting that same parabola at every single z value. So we're getting kind of this parabolic shaped sheet going this way. Notice it doesn't have any circular parts. None of the cross sections are circles. That would be one hint that this isn't going to make it any simpler to deal with in cylindrical. The other would be the integral of y equals x to the 1/2 or x equals y squared is not hard. That's a power rule problem. So it's not like it was hard. It would be hard to work with to be in the beginning. So we probably wouldn't do this conversion in calculus applications, but we can, right? Y squared equals r squared sine squared theta. X equals r cosine theta. I could divide both sides by r since r is in both terms, and then divide by sine squared. And I have r equals cosine theta over sine squared theta, which is cosecant theta, cotangent theta. And so we can integrate that as well. Remember, that's one of our memorized integrals from last year. The integral of cosecant theta, cotangent theta is not difficult. but neither is the integral of y equals square root of x. So there's not really a point calculus application wise. If I don't see circles as a cross section, generally I'm not going to probably convert unless I'm being asked to. Okay, I'm not going to do it to simplify something. Okay, going the other direction is not going to be very applicable in calculus. You should understand you can, how to do it, but most of our stuff we're going to get integrals in rectangular, x's, y's, and z's, and we're going to want to say, this is really hard in x, y, and z. Maybe it would be easier in cylindrical. We're rarely going to see it the opposite direction, but we can convert. So here, I see a cosine 2 theta. That's going to cause issues because none of our conversion formulas have a 2 theta in it. My computer's not charging. Well, so I'm going to use a trig identity. In general, again, I'm not super concerned about you memorizing, but being able to apply. So seeing that cosine 2 theta, knowing that there's a trig identity and looking it up. You might want to put some trig identities in your notes, some of the basic ones, like off the pre-cal memory sheet we gave out last year, those types of ones, just in case you come up on a test and you have a sheet where you can just flip to and say, what's that identity again? This one is cosine squared theta minus sine squared theta. And now I could distribute the r squared. R squared cosine squared theta is just x squared. R squared sine squared theta is just y squared. Okay, and at this point we would be done. Okay, we really wouldn't have to do anything else. If we wanted to put that in a more recognizable form from yesterday, this would be negative x squared plus y squared minus z squared equals 1. That's one of our conic quadric surfaces. And notice it's like an ellipsoid, except 2 of the things are negative, which means it's a hyperboloid of 2 sheets. And since the y is the only positive, it's a hyperboloid of 2 sheets opening along the y-axis. So it's those 2 little cups opening out sideways along the y-axis. Again, it's not asking you to graph, so you don't have to graph it, but if you can kind of recognize that, that's good. Oops. All right, we get out at 11:30, so just want to make sure I don't take over your time. Okay. Spherical coordinates are harder, mostly because you have less experience. You guys have seen polar, and cylindrical is not a very big leap from polar. Spherical is different. Spherical is obviously good for graphing spheres, or things that have cross sections that are spheres. So x squared plus y squared plus z squared is in there somewhere. In a spherical coordinate system, we have our 3 values, just like we do in cylindrical, just like we do in rectangular. Only this time it's a rho, a theta, and a phi. Rho is the distance from the point to the origin in 3 dimensions. So it's similar to r, but remember r we're measuring in the xy plane, the distance. Rho is in space. So think r is kind of like the radius of a circle. Rho is like the radius of a sphere. Okay, and that should be a positive value. Theta is the same angle used in cylindrical when we're using positive r's. If you graph on a calculator in polar, it'll sometimes give you negative r's, and that will make the theta weird. We're talking about theta used where r is positive. So from the positive x-axis going counterclockwise around. So same exact one from cylindrical, so usually that one's pretty easy. Phi is the angle from the positive x-axis and the line segment OP, meaning if I were to connect P to the origin and measure the angle to the z-axis, that's what phi is.
Mr. Smith.
Yeah.
You said x-axis and it says z-axis on here?
Z-axis. It's z-axis. Sorry.
Z-axis? Okay, thank you.
Yeah. Between the positive, I'm so used to saying x because of theta, but no, it's from the z-axis. Okay, and it should be between 0 and pi, because it's always going to be like, no matter where you are, your angle to the positive z axis will never get bigger, because as I move over here, I would just measure the angle on the other side. So it's going to be 0 to pi. So I put the diagram here. There's also one on the next page. So like if you're looking at the notes, there's this diagrams on there as well. This has all of it. It has polar, it has rectangular, and it has spherical. The spherical ones are my phi, which is again the angle from the positive z-axis down. Okay, it's got my rho, which is just the distance to the origin. And then it's got my theta, which is the same theta we use in spherical. I mean, sorry, in cylindrical polar. So that'll kind of triangulate us to a specific point in space, just like an x, a y, and a z will, and just like a r, a theta, and a z will. We can get ourselves to somewhere in space specific. Okay, so I'm going to go over where we get the conversion stuff from. So in this picture, this is a rectangle here. Okay, because of perspective, it obviously doesn't look like a rectangle, but notice we're just going straight over, straight up, straight back, and straight down. Those are a bunch of vertical and horizontal lines. That's a rectangle. Okay, so when we're looking at this picture, these are right angles. So all of our stuff comes from right triangle trigonometry. So if we look at this right triangle here, okay, notice since that whole thing is a rectangle, if this side is z, this side is also z, right? They're the same length. So if I look at that triangle, r squared plus z squared equals rho squared. Well, we already know r squared, that's the r from cylindrical. That's x squared plus y squared plus z squared equals rho squared. So we could use the distance formula. We could use right triangles. Rho is going to be the square root of x squared plus y squared plus z squared. Remember, it's the radius of a sphere. It's the distance formula in 3 dimensions. However you want to kind of think of that, where it's a distance. Theta is the identical theta that we had before, so we could use the same thing. Inverse tangent of y over x. Okay, same theta as we have in polar and cylindrical, so we'll just use the same thing there. For phi, I'm going to look at this triangle. Okay, and I'm going to use that the cosine of phi should be the adjacent side z over the hypotenuse rho. And so if I want to find phi itself, I'm just going to do the inverse cosine of z over rho. Only I'm going to use the square root of x squared plus y squared plus z squared for rho, since we're really trying to get a formula where I can plug in x's, y's, and z's and get out the spherical parts. So again, don't worry about memorizing. Just make sure that you can kind of apply these things. If you have it written down somewhere, you can use that and just make sure you understand what the parts are, what they mean, so that you could actually apply it and use it. Okay, going the other direction, which again, this will be the less common thing. We're usually going rectangular to spherical. Oh wait, I didn't change the words. No, okay, yeah, sorry. We're usually going to convert that way. So spherical to rectangular, I want to basically take some rhos, thetas, and phis, plug them in and get some x, y's, and z's. Again, we'll use those right triangles. I'm going to use the top one for all of it, though. Okay, remember, this is a right triangle this way. And remember, since that whole thing's a rectangle, if this opposite side is r, this is also r. And so I use that sine phi. It's going to be opposite r over hypotenuse rho. So r equals rho sine phi. And so I'm going to use that in my cylindrical polar coordinate stuff to say, well, x is r cosine theta. Well, r is not a spherical thing, so I'm just going to plug this in here so that I can use all spherical values. So rho sine phi cosine theta will give me my x. Y equals r sine theta. And so I'm going to do the same thing and plug in a rho sine phi for r, and then just have your sine theta. And then like we used just on the last page, cosine phi equals z over rho. So z equals rho cosine phi. So I can just use rho cosine phi to get a z coordinate. Okay, so those are formulas that I could plug in spherical and output a rectangular equation. Okay, we see spherical far less. So it's good that we're more comfortable with cylindrical because we'll see a lot more cylindrical polar stuff. Spherical, we have fewer equations where it applies in calculus to making it simpler. The first would be obviously a sphere. Okay, spherical coordinates are great for spheres. If I do rho equals a constant, I will get a sphere centered at the origin. So rho equals 2, sphere with radius 2. Rho equals 5, sphere with radius 5, centered at the origin. Just like with cylindrical, if I do theta equals a constant, I'll get that vertical plane going through the z-axis. Okay, since the theta is the same in both, your theta equals a constant will give you the same thing in both. And then phi equals a constant will give me a cone. Because if we really think like every point on the cone kind of lies on this line that's just kind of rotated around. So if I pick points on the cone, the angle to that line is the same. So if I do phi equals a constant, I'll actually get a cone. You'll only get one part. So where we get the upper and lower cone in rectangular, here I'd have to specify, do I want that angle or an angle down here to get the bottom cone? It would be a different angle. Okay, so I won't get both. I'll just get literally the top or bottom of a cone. So if we don't have something like those things, I don't usually convert to spherical. So we don't use it as much because we don't see as many things that are simplified by spherical. But we can convert. So again, this is a cone. So from yesterday, this meets that it's a cone. Which means we should get a constant as our spherical equation. We should get phi equals a constant, sorry. So if we plug in x squared plus y squared, that's rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta equals rho squared cosine squared phi. And right away, it's like, that's not simpler. True, but we can simplify this quite a bit. One, there's a rho squared in every term, so I could divide by rho squared. Okay, and then notice on the left, we could simplify this by factoring out a sine squared phi. And what we're left with is cosine squared theta plus sine squared theta. Well, everyone should recognize cosine squared theta plus sine squared theta is 1. Right, so this is just sine squared phi equals cosine squared phi, which you already kind of should know where sine and cosine are the same. If I'm squaring it, that just means where they're the same absolute value. Okay, or we could solve this as tangent squared phi equals 1 if I divide by cosine squared, which means I'm looking for where tangent phi is 1 or where tangent phi is -1. which is happening at phi equals pi over 4, or phi equals 3 pi over 4. Oops. So again, each one would give me one of my two cones that I get from that one rectangular equation. If I go pi over 4 down, that's not a great cone, sorry. I would get this one. If I go 3 pi over 4 here, I'm going to get the bottom part. So I would just choose, if I only want the top, I would choose one. If I want the bottom, I'd choose the other. If I wanted both, I'd have to list both. This is theta equals this and this. All right, we're out of time, so I'll do the last few tomorrow. They're just more examples. So it's possible that with the stuff we've gone over, you could just finish them yourself, but I'll finish them tomorrow at the beginning of class. And then we'll be done with chapter 11, and we'll be moving into calculus. So 12 will be derivatives, which derivatives are really easy. Integrals are where it gets a little complicated. All right, so I will see you guys tomorrow, and we will start chapter 12. And you guys have a good afternoon.
Thank you,
You
Mr.
too,
Smith.
thank you.
Bye, y'all. What's happening? Why is my